Welcome to Chemistry 1106 Experiments That Matter for Texas Tech University. Today we're going to be going over experiment number 3, which is the properties of hydrocarbons. This experiment will be in 3 parts. We'll be testing the physical properties of our hydrocarbons, we'll be reacting the hydrocarbons with bromine, and we'll be doing a potassium permanganate test for the unsaturated hydrocarbons. We'll also be using 4 compounds during this experiment. We'll be using methanol, which is right here. We'll be using hexane, which is right here, 1-pentene, right here, and toluene, right here. First, we should define hydrocarbons. Hydrocarbons are compounds that only have carbon and hydrogen, as their name might suggest. Methanol is not a hydrocarbon. It has an oxygen atom in it, so we do not have that under this definition. But the other 3 compounds that we just discussed actually are hydrocarbons. Now, one of them, specifically the hexane, is a saturated hydrocarbon. This is also known as an alkane. This has all single covalent bonds between the carbons, thus freeing up electrons for hydrogens. Hence the name hydrogenated, that comes from the hydrocarbons being saturated with hydrogens, i.e. full. There are lots of different hydrocarbons that are saturated, and we'll talk about those in a little bit. Unsaturated hydrocarbons are those with some double bonds between the carbons, which means there are fewer hydrogens on the actual molecule, and so it's not saturated or unsaturated. They are known as alkenes with an E. There's also aromatic hydrocarbons, named for their very obvious smells. They are made of benzene rings that may have additional molecular groups attached to them. Toluene is an example of this. So these are specifically ring-type hydrocarbons. They look like rings, and they form the basis for a number of compounds that you may be familiar with that may or may not be hydrocarbons, such as cinnamic acid, which is responsible for cinnamon smell, benzaldehyde, which is one of my personal favorites, and that's responsible for the maraschino cherry smell. So those are not exactly hydrocarbons, but they're based off of hydrocarbons. Okay, so looking at the actual experiment, part 1 we'll be performing those physical tests, and we'll be looking at the odor of everything except methanol, which is dangerous to inhale. We'll be doing this by wafting. We won't actually take a big whiff of it. We want to carefully waft it with our hand towards our nose. And we'll be testing flammability, and this will be done in the hood away from other organic compounds so we don't accidentally light the place on fire. We'll be testing solubility in water using test tubes, and we'll be testing solubility in each other. We won't use methanol for this because there's really no point, because it is actually polar, and we'll find out why that has an effect. So we'll also be looking at the second part of the experiment. We'll be looking at the reaction of each hydrocarbon with bromine. This is known as halogenation, from the halogens, and specifically bromination. This is very useful for reasons we'll see in a little bit. The third part of the experiment will react each hydrocarbon with potassium permanganate. This is a test for saturation or unsaturation. Okay, so a few safety concerns. For personal protective equipment, we'll be actually using gloves this time. We'll definitely be using sleeves, goggles, and apron as usual. Potassium permanganate is an oxidizer, so it's really bad for the eyes and skin. You definitely want to keep it off of you. Make sure you clean up spills immediately on all of these, but potassium permanganate is pretty nasty. Bromine is also really nasty. It's got corrosion. It's very corrosive, very toxic, so bad for the eyes and skin, again. And methanol, hexane, 1-pentene, and toluene are all flammable and toxic. Again, bad for the eyes and skin. You might see a pattern here. Don't get it in your eyes. Don't get it on your skin. Let's talk a little bit about beyond the experiment, why this experiment is useful. The first part, we can see that there's a lot of different aspects of physical properties of these compounds that are interesting, specifically why oil and water might not mix, as well as differences in flammability and odor. And the second part of the experiment gives us an idea of the structure, which can be used to identify compounds in real life. Bromination is very specific in the way it attaches bromine ions to compounds. Interestingly, if chlorine were used instead of bromine, the effects would be quite different, as it is much less specific. It wouldn't give us quite as much of a clue. So bromine, the very choice of the bromine atom is very specific to this. And finally, part 3 of the experiment can show us the difference between saturated and unsaturated compounds. This can be used in food science to test saturated and unsaturated fats. such as butyric acid, which is up there, which is right here. And we also have this one here. This is linoleic acid. This is often found in peanuts and things like that. These are two very specific compounds I picked. This one's in butter. This one is in peanuts, and you can see that this one doesn't have really any double bonds between the carbons here. It has a double bond between the oxygen, but that doesn't count. Whereas this one has several double bonds. So this is saturated, or this is unsaturated. This is saturated. Hence why butter is not as good for you as peanut oil.